Okay, again, good morning to new students. Let me start with the stuff that we have left it in a previous lecture. So, in a last lecture, we have discussed about the stuff which is a general register organization and that this selection field and this diagram we have discussed. Okay, and we have get several examples that if such type of the condition, then what type of the stuff is available. If this is a condition, then what type of the line is get selected. And after that, I have given you one example of that to design a stuff related to uh, let me just show you. Yes, stuff related to design a such type of the binary code and related register sequence table, as well as ALU operation. And that exercise we have done for the question like this one, which is having a 16 registers are there and 32 operations are there, which is offered by ALU. One shifter operation with the one shifter block is there with the 8 operation, and how we can design the table for that. That is the stuff we have discussed. Okay, so if we can identify their control words, so this is also we have discussed, like what is the size of the register bit that you require. So obviously this is a 16 bit, so we required a 4-bit selection line to select those 16 bit in a mux, as well as we required 5-bit of ALU. Why? Because there are 32 operations, and we required the 3-bit of the shift because there are 8 operation is there. So this all are 2 raised to power, and according to that number of register block, or we can say number of bit length, which is going to be decided like this one. So we required a 20-bit to do this all the stuff. Okay, so going forward from that, today we need to discuss about that what is the stack. Okay, and we need to give the organization of the register stack with all necessary element, and we need to explain the working of push and pop operation, or push and pop type of the condition. Okay, so this question has been asked many times continuously from 2015 to 2019, and there are another stuff is also, or another type of the question similar to this one is asked, like explain the register stack and memory stack with a neat sketches. So in other term, like in remedial also, that's December 15, 16 and 18. So that's the most important question that we can say that is asked by the GTU in a repetitive manner. So we will discuss about the stack organization. So if we can say stack is a collection of the register or the memory location which is used to store the information. The simple stack is nothing but collection of the register. So there are a bunch of register is there, register or memory location which used to store the information. You can say like that, whatever the stack we have, whatever the stack is there, like you can say book stack, or we can say there are kind of the several book that you are just stored in one on another, one on another, like that. So that we can say the book stack or any particular storage stack. So there is the same type of this stuff. If you are putting your register one by one, and in one, then second, then above, the third, fourth, fifth, like if you're creating a stacks of them, then it is a storage place, we can say. So it is a stuff like FILO, philo. So first in, last out. While stack pointer, it is a register to store the address of the stack, which points at the top item in the stack. Okay, so stack pointer will be the register which is store the address of the stack, which is a point, and we can say stack pointer it is meant which is point out at the first location, or we can say at the top of the stack. Okay, and one by one it is get increase and it's going down, 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 like that. Okay, and this is called as a top of the stack. So stack pointer is pointed out at the top of the stack, and by increment this one, it is going to down, 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 and one by one memory location get executed from that. Okay, stack can be placed in the portion of large memory, or can be organized as a collection of register inside the CPU. Okay, so stack, that we can say consider it's either a part, or we can say it's one of the portion of the large memory. Okay, That is also required many times whenever you are arranging a register inside your CPU. So as you can say in our 8085, that example that we are taking, so it is having a B, C, D, E, H, L register. So we can say there are a stack of register pair, which is denoted as a B, C, D, E, H, L. So that is either the collection of register inside of CPU that is used for temporary storage or permanent storage, ROM, RAM, in any type of the meaning of that. So this is a overall stack organization. Like there are a stack starting having some address, then it is having kind of the stuff related from 0 to 6 and like this one. And we can say there are a block diagram of 64 word of this stack. So starting on the 0 and then 1, 2, 3, 4, 63, it's stored in a 1, 1, 1, 1, 1 above like that. And there are a stack pointer, its content of stack pointer is now 3. So whenever there is a value SP, according to that, their number is going to be increased, and according to that, their pointing out is also going to be changing with respect to the that is going to be changing with respect to the increment of the particular number. Okay, so if you can say stack pointer is 23, so that arrow is go to 23. Over here, there are a data register is there. So data register is nothing but how the stack is going to be look like. So it's kind of the stuff like wherever the stack pointer is pointed out, and whenever you just on their tri-state buffer, so from that register location, and register, you know that it's a set of flip-flops are there, it's a group of flip-flops are there. So whenever you are giving a enable to that tri-state buffer, the data which has been stored by that flip-flop is going to given to your data register. So stack pointer will give the point out that at which location you need to start accessing the data. So whenever the stack pointer is pointed out, their tri-state buffer is get enabled and data is going to either load or it's going to be stored. Any type of the stuff that going to be happening. Okay, so this is a thing is going to be there. Just a second. Okay, so this is overall register stack organization. Now in the same stuff, there are a example of that one. Okay, so stack pointer is contain a binary number whose value is equal to the address of word that currently top on the stack. The 1 bit full is set to 1 when the stack is going to be full, and the 1 bit register empty is set when one stack is going to be empty of the data. Okay, as well as 3 data are placed into the stack A, B, and C in that order. And DR is the data register that's all the binary data to be written into or read out of the stack. So that I have said you like it's how it's going to be work. Like whenever you pointed out with any number with the stack pointer, let's take your stack pointer is 63. So your stack pointer pointing location go to 63, and over that 63, whatever the data register you have, and according to that read or write signal you have given, so that tri-state buffer is getting on or on off, or it's going to either in read mode or write mode. The tri-state buffer is getting enabled, and your data is either going to load or it's going to be stored, or you can say read or the write. And according to that entire stack, if the entire stack is empty, then empty bit is going, empty flag is going to 1. And if there are a 1 bit register full, if their entire stack is getting full with all the memory, then it will show that there are all the stacks are full in this particular section, so it will showing the stuff like that. Another we have instruction related to push, and we can say the pop. Okay, so what is inside the pop, what is inside the pop, that we need to discuss over here. So to insert a new data, the stack is pushed by incrementing SP and writing a word in the next higher location in the stack. Okay, so if stack is not full, so first condition we need to do that stack is not full. It means full bit must be a 0. It means there are some places are there we can say there are some space are there which is already available in your stack organization, and your every location is not going to full now. So what you need to do, if the stack is not full equal to 0, a new data can be inserted with the push operation. Okay, the push operation will consist the following sequence of the microprocessor. So we can say behind of this push, this is overall stuff is going to be working behind to that instruction. So push is used to insert a new data in the stack location. Okay, but what's the condition? Full bit should be 0. It means that there are some space are there which is available in your register stack. So whenever you write a push, what happened? Stack pointer get increment by 1. Let me take a laser pointer, so it's going to be, so stack pointer get increment by 1. Write item on the top of the stack. You need to, whatever the data register is there, the data register value is stored in the pointed out the stack pointer location in that stack memory. That data is going to be stored over there. If stack pointer is getting 0, then you need to make your you need to check your status. If SP equal to 0, if stack pointer is going to be 0, then it's considered as it's all the full. You need to set as a full equal to 1 and make empty equal to 0. So what is the meaning of that? Like you need to check if your SP is 0, like you are adding some data, like you are adding a push continuously in your program, in your assembly language program, you are continuously saying push like that. So after doing the inserting the memory over there, inserting the data in that stack memory, you check that whether this stack pointer is a last location of your overall program or not. So if stack pointer is a 0, it means it is a last location. It's meaning of that your entire stack is now full. So you directly says that full equal to 1. So whatever the next instruction is there, which will get the idea that right now it become a full. So no other push operation is going to be executed. But if it is your SP is not equal to 0, it means your stack pointer is not 0, then you need to say that it is still empty. Your stack pointer still having some kind of the empty location, and there you can store the data over there. So after every execution of the push, you need to check whether there is a last location of the memory or not. If there is a not last location, you need to make your empty flag equal to 0. Otherwise, you need to make it full equal to 1. So it is indicating that whether there is a next push can be executed or not. Okay. So this is a micro operation sequence going to executed behind the push. Next, we have a pop. So that pop is a inverse of that. Okay, in push we are inserting the data in a stack memory, while in the pop we are getting the data from the pop memory. So data C is on the top of the stack. So we can say the data content of SP is now 3. The remove the top data stack is popped by reading the memory word at the address 3 and decremented the content of SP. Okay. So we can say if the data B is now on the top of the stack, since SP is hold as address 2, a new data is deleted from the stack if the stack is not empty, if empty equal to 0. So what are the things we have? We will just discuss directly with their program locate or that micro program instruction. So it will be like that. When you write the pop, whenever you write the pop, so whatever the stack pointer location is right now, let's take it is in a location number C, it's location number 3 SP. So what it will do, from the location number 3, data is a C available over there, so that is going to load into your data register, and then stack pointer decrement by 1, then it is go to the number 2. Okay, if that is going to be in a number 2, and again it will check if the SP equal to 0, if it is going to be checked that if that stack pointer is equal to 0, it means is it the last location of getting the data from the memory. If there is a last location, then you need to make it is a empty equal to 1, otherwise you need to make full equal to 0. So what is the meaning of this 2 line? Okay, you are just getting a kind of the decrement one, like 3, 2, 1 like that. if you can see that our previous PPT, you can get the idea. Like it is going to check like that. Right now my stack pointer is over here at C. And if I just do the pop, so what it will do, the C will come to your data register and the data is going to given to your CPU. Then that stack pointer decrement 1 and it is reached over here. Then over at that location it will check what is the value of stack pointer. Right now it is a 2. Right now it is a 2. It means this is not a last location. So this is not a last location. It's still 2. So what you need to do over here, you need to do that your empty is going to be 1. It means if your stack pointer is not equal to 0, then you need to say that full equal to 1. So इसका मीनिंग क्या हुआ कि अगर आपका लास्ट लोकेशन नहीं है, मतलब कि अभी कुछ डेटा वहां पे पड़ा हुआ है, मतलब कि अभी पूरा डेटा फुल नहीं है. So you are making full equal to 0. So you can say there are a still scope of getting the data from your stack pointer, stack organization, sorry. But अगर आप last date पे पहुंच गए हो, if you are saying that it's at the last location your stack pointer is right now, so you make your empty equal to 1. It means आप डेटा एक्सट्रैक्ट करते 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 C में से, B में से, A में से लास्ट में आ गए and your stack pointer becomes 0, then you need to say that now your entire stack is getting its entire stack pointer is getting over and all the data is going to be retrieved back. So you can say you need to make your empty flag equal to 1. Okay, so push में क्या करते थे, हम चेक करते थे कि जब तक पूरा स्टैक भर नहीं जाता तब तक हम उसको क्या बता देते थे कि भाई खाली है, खाली है, खाली है. How you can say that this खाली and that's empty? By making this empty equal to 0. It means still location, still location, still. Once it is fully done, then you make full equal to 1. Similarly, there are a reverse case. You are saying that it's a field, like it's full equal to 0, 0, 0. It means still there are data is there, still there are data. Once all the data getting done, then you make empty equal to 1. It means now all this stuff is empty. So this is a pop location. Any doubt in this one? Anybody? Any doubt? Any question in this one? Yes or no? Tell me. Push, pop, and the stack pointer. Stack pointer is nothing but sequence of register has been stored in a stacking manner. To point out the location, there are a stack pointer is there, and the data is going to be loaded by data register. So whenever the stack pointer pointed out, and whenever there are a read or write operation is there, your data from data register to that location or location to data register going to exchange. And whenever that data register is, whenever the stack pointer is going to full, then there are a full register getting on, and if entire stack pointer is getting blank, it's become empty, then empty flag is going to be there. And according to that, push and pop instruction is there. Push, it means you are adding the data in stack pointer until and unless it is not getting filled. And pop, it means you are getting the data from the stack register until and unless it is not become the empty. That's the simple overall concluding remarks over here. Is it clear with everyone? I have a 32 student. Yes, Arman Ali, tell me, Arman.
Yes, sir. सर अगर हम दो डेटा के बीच में कोई डेटा पुश करना चाहते हैं तो कर सकते हैं इसमें.
दो डेटा के बीच में, yes. For that, Arman Ali, you need to make your that stack pointer location at the different kind of the location. You need to make it jump. Okay, like आपको कुछ बीच में डेटा छोड़ देना है, लेकिन आपको कोई और डेटा लेना है उसके बीच में. So you need to control your stack pointer. You need to artificially give your stack pointer at another location. ये हम करते ही थे ना. Like there are some instruction is there where stack pointer location or program counter location is getting just it's getting to that somewhere else, and the data going to be stored over there. आप ऐसा कर रहे हो कि आप ऐसा, मैं पहले पुश कर दूं कोई डेटा, मैं वहां पे पुश कर देता हूं, मैं वहां पे रख देता हूं, लेकिन आफ्टर दैट माय पॉइंटर आई विल सेट इट टू अनदर लोकेशन. कुछ इंस्ट्रक्शन, असेंबली इंस्ट्रक्शन को यूज करके मैं अपना प्रोग्राम काउंटर कहीं और पे लेके जा रहा हूं और वहां पे मैं पॉप करना चालू करूं. तो क्या हुआ, डेटा आपने कहीं पे स्टोर किया, आप रिट्राइव कहीं और से कर रहे हो. सो यू कैन से देयर आर अ गैप बिटवीन बोथ ऑफ द मेमोरी लोकेशन, बट यू नीड टू समहाउ चेंज देयर पॉइंटर लोकेशन. Then it's going to possible. Okay, so if you just manage that stack pointer location, then you can in between data आप उसको रख भी सकते हो उसको छोड़ भी सकते हो, दूसरी जगह पे जा सकते हो, like that. But once entire data is going to be off, then you must make that flag empty on, or if that entire location is full, then you need to make that location full. यही होता है ना जब आप कोई ड्राइव बनाते हो, whenever you making some drive, and if all you are adding the data over there continuously, and there are some limit is there. Once that all the data is going to be filled over there, it will give you the indication that you not have the sufficient memory location to store this data. So कैसे पता चलेगा कंप्यूटर को कि अभी sufficient location नहीं है? क्योंकि आपके पास जो डेटा का साइज बचा हुआ है उससे ज्यादा आप वहां पे रखने का बात कर रहे हो. So initially it will check whether that stack pointer is empty for that or not. So likewise, that stuff is going to be happen. Okay, so whatever this small stuff is there, it is actually used in your real life. Whenever you are just over copied some of the stuff into small locations, so that stuff is going to be happen. At that time, it will give the indication. Yeah, it is possible. Armanali, you need to just manage this stack pointer. Any question to anybody? Is it clear? We have 32 students over here. I need a confirmation from everyone. Yes or no? Clear, not clear? This is a 7-mark question. Okay, this 4 to 5 slide will give you the 7-mark answer. So think accordingly. Clear. Okay. We will move further for the next step. So this is a stuff will be like that. Memory stack organization, how that computer memory with program data and all the stuff has been stored. So it will be stored like this one. Okay. So initially there are a program instruction is there, then data is there that we can say the operands, then there are stack pointers are there. Okay. So stack grows in this direction. Stack is going to be grows in this direction, while program instruction that you can assign like in this manner. Okay. So we can say first there are a highest number of the stack, then lowest, like that. The stack location we have discussed in a previous slide. While program instruction that we can give it from kind of the 1000, 1001, 1002, and data will be also stored like this one. So this is a program counter. We can say that's the address that register, or we can say stack pointer. So there are 3 pointer are there, and it is going to be stored in this hierarchy manner. Initially stack, on the top there are a data operands are there, and on the top there are a program is there that actually you have loaded in your system. So that's the overall thing we have. So memory stack, program counter point at the address of the next instruction in the program, which is used during the fetch phase. So वही हम करते थे ना, fetch, decode, execute. So from the program memory, it is getting fetched, decoded, and according to the direct memory address, indirect memory address, whatever the operands you have, that is going to be getting from your data location. Like what is the address register? According to that, you are getting a data from that, operands from that. Okay, and then it is going to give that stuff to your system, and all stuff is going to be work. So program is stored over here, related to that data operand is stored over here. Okay, so what is the thing we have? Like the program counter point at the address of the next instruction where the instruction has been stored, in which it's during the fetch phase to read the instruction. The address register point at the array of the data that actually you used during the execution phase. Okay, so program के लिए जो instruction है वो आपके program counter से point out मिलेगी, लेकिन किसके ऊपर वो program करना है, that you can get it from the address register. Through that address register point out at the data location. So जो भी चीज execute होनी है वो instruction में लिखी है, but वो किस पे execute होनी है वो data operand में लिखी है, that going to point it out by address register. So program counter से जो instruction लिखी है वो ultimately आपको address register का location ही देता है, that what is address register location, that you take the data and then it's going to be executed. So the stack pointer points at the top of the stack, which is used to push and pop items. Like you record that whatever the data right now you have, you just pop out or push out at temporary location. So whenever you just do the push and pop, that data, whatever that generated data from your system, it's going to be getting stored in your stack pointer. Like कोई आप instruction लिख रहे हो, like कोई memory instruction है, after that if you have, there is a push, you have written the push in assembly language program. So whatever the data that you are storing during that push instruction, it is going to stored at the over here. And as much as time you push, give, the data is going to be stored over here, and down. We can say in that manner. Okay. Whenever you're doing the pop, so one by one, the data is going to be get back. So if you have initially given a 3 push, so a stack pointer will we can say stack pointer is going to be stored like that. And whenever you have pop, so from that location, it is getting retrieve those data back. After push kiya hai, so it's stored, let's take in a 30, 3001, 3002. When you say pop, it means it will first take the data from 3001, 3002, 3001, 300 like that. तो जैसे push करते हो तो नीचे जाता है और data store होता जा रहा है. When you pop, when you make that kind of the pop, so it's retrieve back and reach to their original location. It's like a spring. If you are giving a pressure, it is going down. When you release it, it's again come back. So its data is stored like this one. When you're giving the push, data going to be just a spring, squeeze and stored. When you just release that through pop, it's going to be retrieve back those data and reach to their original position. Likewise, this stuff going to work. So next we have what are the 4 type of the instruction format we have. Okay. Opcode, address field, mode field, that already we have discussed many times, but in that detail, that are the stuff that we need to discuss over here. Up to this particular stuff, any questions to anybody? Yes, no, anything we have? You have any question? No? We will go with the question. Explain the 4 type of the instruction format. Okay. So instruction format, you are having basically opcode, address field, and mode field we have. Okay. So in instruction format, what are the things we have? Like in opcode, we can say specify the operation that you're supposed to perform over there. Okay. Specify. Just a second. Specifies the operation that to be performed, like which type of the operation you need to perform, add or okay, X or X not, that we can say the operation that you perform. Then the address field, like it's a designated memory address or a processor register. So whatever the operation that you want to perform, on which particular or we can say on a which particular point out, or in a which particular operation, or on which particular data those operation need to perform, which is given in that address field. That another stuff, mode field, specify the way the operand or the effective address is going to determine. Okay, so there are 3 box we have: opcode, mode, and address. So we will see what are the things inside of that. So there are 4 we can say instruction format: 3 address instruction, 2 address instruction, 1 address instruction, and 0 address instruction. So that's related to 0, 1, 2, 3. So how many type of the address instruction we have, that we need to study over here. So we can say 3 address instruction will be like this one: add R1, R2, R3. So that's the one type of the possibilities is there. Directly you can say whatever the first location, it's your destination, and rest of them it's your, we can say, operation that on which you need to do. So whenever it is like this one, add R1, R2, R3, so resultant data come to R1 and addition is going to be done on the next 2 bit, or we can say next 2 register, R2 and R3. 2 address location will be like this one: add R1, R2. It means you need to do the addition of both one and you need to store it to the R1. Add R1, R2. So we can say first you need to do the addition of both of them, and whatever the answer is there, you need to store into the first kind of the address that notation you have given over here. Like move R2, R1, R2 data come to R1, add R1X, memory location of that one come to the R1 data store in R1. One address instruction that mostly that we are using in our 8085, which is like this one, single accumulator, which is add X. So whatever the data is there, which is one data must be stored in accumulator. So whatever the data you are giving, that data going to be perform that operation, add operation with the accumulator, and the data again going to be stored in accumulator after performing this operation. So if you are just writing ADDX, so whatever the memory location data is there, it is adding with the previous content of accumulator, and updated one is stored in accumulator again. Like the push X and all the stuff. Zero address will be like this one, ADD MUL. So nothing is going to be given over there, but it's simply written ADD. So whatever the two for that, it's going to be specified like that, what you need to do with that accumulator location. Like another stuff also, you can say when you're writing something, I can say there are instruction related to I can say CIR, RRC, RLC. So we can say with that accumulator only you need to do that. Nothing that external is going to be given on that, or not any register is going to be point out for that. That one instruction is executed on one register only. So that we can say the zero address based stuff. So three instruction address, how this program is going to be executed. So this is one of the example over here. So program will be X equal to A plus B and C plus B. So it will do with the 3-line instruction like add R1. So there is R1 is a temporary location. R1 A B. So the memory location of A, memory location of B, all the data going to add and data store into the R1 register temporary. Similarly, you need to do with the C and D. Add R2 with memory location C, memory location D, and add it to the R2. Then simply you need to do multiplication. You need to store the answer at the memory location of this R1 and R2. So instruction will be multiplication of X, R1 and R2. So instruction becomes long, many bits is required for that, because that are large instruction, you can say. While two instruction, same stuff, how it's going to execute it, it is executing like this one. Like first take the data A to R1, then add that data into the R1. So we can say that whatever the previous content of R1, it's going to be added with the B. Then take the C data into R2, added with the D. So now you have R1 and R2 having the addition of A plus B and C plus D. So R1 having an addition of A plus B, R2 having an addition of C plus D. Then you make multiplication, MUL R1 R2, and then there are data has been stored by the move instruction. So we can say that instruction, that number of assembly line is increased, but to execute the number of instruction is getting increased. So whatever the number of bits you required in previous case, it's reduced, but your length of your program, it's getting increased. One instruction format, it is going to be done like this one. AC register for accumulator register for all the data. So it will be like this one. Load A, then add B, then store into the temporary T, then load C in accumulator, then add with D, then you multiply it with the T, then store into X. So load, add, store. So all this stuff is going to be done with the accumulator only. So every time you need to take accumulator as a reference, and you need to do the load, add, store, load, add, multiplication, all the instruction like this one. So that's the another example of the one address instruction. Zero address instruction can be found in a stack organization in computer. It will be like this one. Push A, push B, add. So once you just push A and push B, when you do the add, so it will do the addition of all the previous one. Then push C, push D, and then add. So it's going to be do the addition of the previous two condition. Then multiplication, so it will do the stuff of previously added result, whatever that in A and B and C and D. And then you pop that result into the location X. So you are taking the data with the push instruction, add instruction. So that's the 1-bit instruction is there, but it can be found in a stack organized computer. Okay, so stack pointer is going to be stack location is used when you are writing such type of the 0-bit instruction. Okay, and that all the data is going to be done with the previously stored one. Like पहले आपने A B को push किया और बाद में add लिखते हो, so it will done with the A and B. बाद में फिर से 2 push लिखते हो और add लिखते हो, so it's going to be done with the previous stored data. When you write a multiplication, so it will done with the previously added data. Likewise, you need to manage of that, or such type of the processor, such type of the instruction set you need to design. Okay, so not that add and mul will be pop the two pop-up number from the stack, adding the number and push the sum into it. So that's I have told you. Add and mul will be take the pop of the previous two instruction. जो भी दो पहले की instruction थी उसके साथ वो operation करेगा. So likewise, that type of the kind of the algorithm or that kind of the control unit you need to design. Okay, so these are with up to this particular point we are going to hold, and whatever the next content we have, that we are going to be discussing in the next lecture. So let me first take the first let me ask anybody having any doubt, like 3 instruction, 2 instruction, 1 instruction, 0 instruction. Okay, 3 register, 2 register, 1 register, 0 register. So these are the difference, and 7 mark question might be asked. So let me just take your attendance first, then we will go with the rest of the things. So today we have started with the chapter number 5, CPU stack organization. Okay, stack organization and instruction format. So start with the numbers. Pick up the number over here, number 37.
Yes, sir.
2, 3,
4, 5, 6, 7, 8, 9.
6,
6,
8,
8,
9,
9,
10 and 7, sir.
7. 10 is there?
Yes, sir.
Okay. 7,
11,
11, 12,
13, 14, 15, 16,
17, 20,
21,
22,
25,
26, 27. Yes. 27, 28, 30, 31, 32, 33.
32,
32, 31, 33, 31, 32, 33, 35,
36,
36,
23% है सर.
23 present है. चलिए 37, 38, 39,
39,
37, 38, 501, 502, 503,
502,
502, 503, 501, no, 504, 505,
504,
505, 506,
Yes, sir.
507,
sir,
508, 509, 510,
510.
511.
yes sir,
So option number is 4, 5, 18, 26, 28, 30, 37, 38, 501, 505, 508, 509.
Yeah.
So
Sir, 38%, sir.
38 present. Next,
505, network is
505. Next, 38 and 505. Option number is 4, 5, 18, 26, 28, 30, 37, 501, 508, 509. Okay. Any present from these numbers? Okay. So please write your summary in the chat box, everyone, and then after you can go. So please write your summary in the chat box, then you can just go and wait for the next lecture. If you have any question in this chapter, you can ask me right now.
सर कल जो क्वेश्चन दिए थे उसका आंसर
वी विल गो इन नेक्स्ट लेक्चर में करते हैं उसका। ठीक है, अभी एग्जाम है उसका, सब बोल रहे थे, तो अभी एक EC2 क्लास में मैंने नहीं दिया है क्वेश्चन,
यस
सो आज
सर
मैं उसको क्वेश्चन दे देता हूँ, बाद में नेक्स्ट वीक में उसका पूरा सॉल्यूशन करते हैं। ठीक है,
ठीक है सर थैंक यू सर
ओके।